Hi everyone. In the last class, we saw what you call as concept of hybridization. Okay, and what is the reason uh, for origin of that concept? Okay, now we are going to there itself we learn the types of hybridations. Okay, and the types of hybridization. First one is the first important one is the SP hybridization. SP hybridization. Okay, now so in this class, just we will complete the SP hybridization. How we'll get this way? SP hybridization. We'll see one way. Okay. Now, now we'll see the what you call as SP hybridization. Okay. So this type of hybridations involves. So this type of hybridization we get. So by the mixing of one s orbital and one p orbital. Okay. So if one s orbital and one p orbital by intermixing, we will get a so we will get a two equivalent sp hybrid orbitals. So already we learned the two atomic orbitals in one hybridization, we will get a two hybrid orbitals. So because of that, so here one s orbital and one p orbital involves. So by that we will get a two equivalent sp hybrid orbitals. Okay. So these two sp hybrid orbitals, so these two hybrid sp hybrid orbitals will have a 50% s character and 50% p character will be there in this two sp in the sp orbitals, sp hybrid orbitals. Okay, so in this sp hybrid orbitals you can see the 50% s character, 50% 50% p character. Okay, now same way, and in the molecule of the central atom. So this sp hybrid orbitals, sp hybrid orbitals, so will this sp hybrid orbital will link to the central atom. So directly they will possess a linear geometry. Okay. So how now? Suppose if the central atom, okay, for example, there is central atom. Around the central atom, just these two hybrid orbitals, sp hybrid orbitals, will so arranges like this in a linear way. Linear way. So in the linear way, these sp hybrid orbitals will orient or link to the central atom. Okay. So maximum this sp hybrid orbitals will possess linear geometry. Linear geometry. Okay. So this hybridization also we can call as a so diagonal hybridization. Diagonal hybridization. Okay. So linear. So this sp hybridization also we can call as a diagonal diagonal hybridization. Okay. So around the central atom, these sp orbitals will orient in the linear in the linear way. The linear way. So they will orient. Okay. Now these two sp hybrid orbitals will point out opposite direction along the for example, if your p orbital is the if the p orbital is the pz orbital. Okay. So what will happen? Just they will orient along the z axis by projection the opposite loops. Okay. So by projecting the positive loops, so just they will give a like this. See, the central atom, for example, the central atom. Okay. So they will be project. So just the so they will point in the opposite direction along the z axis with projecting positive loops. By projecting so large positive loops and very small negative loops. Very small negative loops like this. Very small negative loops. Same with this side. Large positive loop and a small negative loop. Okay. So like that. So they will orient linearly. Okay. Around the central atom. Okay. And they will possess a more effective. This type of orbitals will possess a more overlap, more effective overlap. They will possess a more overlapping, and also, so this sp hybrid orbitals involve the very strong bond. They also involve the very strong just by overlapping with the other orbitals. Whether they overlap with the other hybrid orbitals or overlap with the atomic orbitals, that will depends upon the molecule. Depends upon the molecule. But so I have to keep in mind, only orbitals of the central atom will undergo hybridization, not the surrounding atom orbitals. Okay, only orbitals of the central atom only will undergo hybridization. Okay, so I will explain this concept by taking a small example. So I am taking a small example, beryllium dichloride. I am taking the So beryllium dichloride as an example. I'll explain how this is hybridization and sp hybridization happens in this beryllium. So dichloride. So what is the geometry? It will process. What is the bond angle? It will process. Okay. Now, so in the beryllium dichloride, the central atom is the beryllium. Here beryllium is the central atom, and chlorines are surrounding atom. These two chlorines are surrounding atoms. These two are surrounding atoms. Okay. Now, so already we learned how to identify the how to identify which element is central atom. Okay. So the element which was which have a low electronegativity, so automatically that will become a central atom. Okay. Now here the less electronegative element is the beryllium compared to the fluorine. So that's why it is the central atom. Okay. Now this is the way you can identify the central atoms. Okay. Now, so when you see the electronic configuration of the beryllium, okay. So beryllium atomic number is 4. Beryllium's atomic number 4. So its ground state electronic configuration is 1s2 and 2s2, and 2p are there, but the empty in the ground state. Okay, but in the excited state, so one of electron from the 2s will shifted to the 2p orbital. Okay, so by that we will see the excited electronic configuration like this. Excited state electronic configuration. Excited state electronic form. That is like this. Okay. So one of electron from the 2s orbital will shift to the 2p orbitals. That will be like this. That is 1s2, 2s1, and 2p1. Okay, 2p1. Okay. Now, so by this, so we can say that, so this beryllium has a divalency. So there are two lone electrons at it. Lone single electron, half electrons at it. Okay. So by that, so it will possess a divalency. Okay. Now, so for forming the sp hybridization, already we learned one s orbital we required, one p orbital we required. Okay. Now, so that's why one 2s orbital and 2p orbitals get hybridized and give a 2sp hybridized orbitals. It will give a 2sp hybridized. So this orbital is involved with the hybridization. Okay. This one s orbital and one 2s orbital, one 2p orbital. So involved in the hybridization, by that you will get a 2sp hybrid orbitals will get. The 2 is the number. Okay. The 2 is the number. So 2 number of sp hybrid orbitals will get. Okay. And these two already we learned. These two sp hybrid orbitals are oriented in opposite direction by with an angle of 180 degrees. So for example, see here. So this is the beryllium. Okay. So already we learned. This sp hybrid orbital, they have a same equal energy and same shape also. Okay. So they will orient. So opposite direction with an angle of 180 degrees. With the angle of 180 degrees. So like this they will orient. Okay. Now they won't tell it. And each hybrid orbital have a one electron in them. So there is one electron in them. So they have a half it. There is one electron. So this rearranges. So this already two electrons are there. So that two electron will be rearranged in the hybrid orbital. With the one sp hybrid orbital, with the one sp hybrid orbitals. Okay. So there is one lone electron there that will be arranged like this. Okay. So these sp hybrid orbitals involves in the overlap with the surrounding atoms. Okay. To overlap with the orbitals of the surrounding atoms. Okay. So if you see the surrounding atom, what is the surrounding atom here? The surrounding atom is the chlorine. Okay. So what is the surrounding atom? Surrounding atom is the chlorine. Okay. Here we have two chlorines. If you see the electronic configuration of the chlorine atom, it is what? Its atomic number 17. So 1s2, 2s2, 2p. So totally it will bridge to the 2s, 2p6. Okay. And 3s2, 3p5. Okay. So these are outer shell orbitals. There is the 3s2, 3p5. Okay. So in the 3p, there is a 3px. That is a full and 3py, that is also full error. The pair electrons is there and 2pz. Okay, the 2pz there is only one electron in there. 2pz there is only one electron in the 2pz. Okay, so this chlorine required a one electron for getting the octet configuration concept same. Okay, so that's why this 2pz orbital overlap with the sp hybrid orbital of the beryllium. Get the to form a bond, to make a bond just by overlapping. Okay, so this is what is 2pz orbital. So what is the shape of the p orbital? Dumbbell shape. Okay, so there is a 2p, the 2p z orbital. It have one electron. It have one electron. Okay, same way with other chlorine, same type of 2p z orbital with other chlorine. With other chlorine also there is the same type of orbital will be there at the end. It is 2p z orbital with the one electron. Okay, so these orbitals overlap with the sp hybrid orbitals of the beryllium. Okay, so they overlap like this. Okay, they overlap here. Okay, so they overlap with the this sp hybrid orbitals. Okay, so by that, so already we learned while overlapping. So while overlapping, what happened here? So the electrons get paired with opposite spin. So while overlapping, what happened? The electrons get paired with the opposite spin. Okay, with the chlorine atom, with the other chlorine atom. Okay, so here bond angle is, here you can see the bond angle, there is 180 degrees. This is the bond angle here. Here the bond angle is 180 degrees. Okay, see the shape like this. Okay. That is here beryllium at one side chlorine, here is one chlorine. Okay, now bond angle is 120 degrees, 180 degrees. 180 degrees is the bond angle. Okay, so whenever there is a sp hybridization, so they will possess linear geometry. The molecule possesses linear geometry with a bond angle of 180 degrees. 180 degrees. So whatever the molecule is, the central atom possesses a sp hybridization. What is the geometry? Linear geometry. And what is the bond angle? So 180 degrees is the bond angle. So this is the way sp hybridization will occur. Okay. So this is about the sp hybridization. The next slide will go with a sp2 hybridization. Thank you. Have a nice day.